Hello everyone. In previous concept in the current electricity chapter, I discussed about two concepts. One is relaxation time. So the relaxation time we define as the average time that elapses between two successive collisions of an electron, that we define as relaxation time. So that which symbol gives to tau, relaxation time tau. Average of collisions, successive collisions between two successive collisions. So if it is n number of, we can take the total as n. Now another concept I discussed about the relaxation time. After that, drift velocity v suffix d, which equal to minus e tau upon m. So this is the drift velocity, which is nothing but velocity gained by the electrons in the presence of external electric field, and this drift velocity is opposite to the direction of electric field, external electric field. So drift, the term drift means something like that we need to pull. So try to analyze this diagram which is given in the NCERT itself. Suppose here it is having two lines. One is the solid blue lines, which is solid, and another one is a dashed black lines or dotted. Now suppose if an electron is moving from A to B, the solid blue lines tells about the motion of the electrons in a conductor in the absence of external electric field. It is an hypothetical, it is not a sure at all, but to visualize, to make us better understanding. So it is something like a random path, zigzag path. So if that we take the electron's motion from point A to point B through repeated collisions within the lattice, within the atoms, like that. But in the second case, if an external electric field is applied, so this is the direction of external electric field. Now, the same electrons do not follow the same path due to because of external electric field. You notice a change in small segment of distance, I can say at here, a small segment. Earlier, in the absence of electric field, the electron end up at B. Now due to the presence of electric field, it end up at B dash. Now that difference between the 2 points B to B dash, we can say that a slight drift, electron is slight drift opposite to the electric field. Drift, it's opposite to the electric field. To this drift, the electron had a velocity, so that we defined as drift velocity in terms of minus e times by m. Here lower e tells about charge of electrons and capital E tells about external electric field, and m is mass of an electron, and this negative sign, the negative sign tells about very important, here the drift velocity of the electron is opposite to the external applied electric field. So by taking this concept as understanding, by considering that point, today I would like to talk about another relation, that is relation between electric current and drift velocity. relation between electric current and drift velocity. It means I and V suffix d. The relation between electric current and drift velocity. Now let us understand this first. So for this, I pre-draw a diagram to not waste our time on screen at here. Suppose this is a metal conductor, a conducting surface, so which I am going to highlight. So this is a conducting surface. It is having a free electrons. This conducting surface of length L and area of cross section capital A. It is having length L and area of cross section capital A. This is the area of the conductor. Now to this conductor we applied an external potential difference. So potential difference we applied. So right at here it is positive charge, since it is positive potential, at here negative charge. Now due to because of this positive potential at one end of the conductor, electrons inside the conductor, so these are the electrons which are located inside the metal surface, inside the conducting surface, they started to drift, they started to move towards the positive plate. Now why they are starting to move towards the positive plate? Because an electric field is set up between the ends of the conductor. So first I need to write that how much electric field is set up between the ends of the conductor. So the electric field set up between the ends of the conductor. So we know that electric field and potential relation. Here the V is the potential, electric field, otherwise you can remember this formula. I always do potential V equal to E times D. So this is the potential, electric field and distance relation in the capacitor plates. So if V equal to ED, so here also same formula, potential V equal to, I can write that potential V equal to E times, here the D is nothing but L, length of the conductor. Now from this expression I can write that electric field setup between the two ends of the conducting material E equal to V upon L. So this is the electric field and potential and the length of the conductor, that is relation. So remember this relation. So how did we get? We got that the relation between potential versus electric field between the plates of a capacitor. Here instead of the distance between the two plates, we have taken as length of the conductor. Now under the influence of this electric field, the free electrons began to drift in the opposite direction of the electric field. So they are having a drift velocity Vd. So that point keep in mind. Now what shall I find? First I need to find about current. What is the current relation? We can write current I equal to Q upon T. So first I need to find that what is the amount of the charge present in this conductor. Now for that, let the number of electrons per volume or electron density, let me take that short word at here, let electron density or electrons per volume, let this electron density equal to small n. If n is the electron density, because this conductor is a three-dimensional surface, it's not as one-dimensional surface, it's a three-dimensional surface, it's having length and it's having the area, so obviously we can get that volume. So electron density equal to capital small n, and charge of electron equal to small e, little e is the charge of electrons. Now I need to find how many electrons are present in the conductor. Therefore, if you can change the color, number of electrons. I'll use electron for the E minus, you follow that. Number of electrons in length L of the conductor. If L is the length of the conductor, what we consider at here, and A is the area of cross section. So try to get the what is the number of electrons in the length L of the conductor. So from here you can get it. If small n is the electron density, so to get the number of electrons of length L of the conductor, what we should do? We should multiply the small n times volume of conductor. So the total number of electrons we can get small n times volume of conductor. So here we can get it. If small n is the electron density, I want to get the total number of electrons. It's simple. You have to multiply that electron density times total volume of the conductor. So if I can take this as small n times volume of conductor means nothing but area times length. So many symbols are there. I will reduce n times AL. Here A is the area of the conductor and L is the length of the conductor. A is the area of the conductor and L is the length of the conductor. Now for the next, that the total charge contained in the total length L of the conductor. So the conductor I have taken here, the L is the length of the conductor, and now I want to find what is the total charge. Now if I can write that at here, the total charge on length L of the conductor. So how can I get the total charge? Total charge Q equal to charge of electrons, and how many electrons are there? So this is the count. Total n is the number of electrons times area times length. Now charge of electron times n times AL. So this is the total charge on length L of the conductor. Now that is the quantity of the charge we got it. So this is the amount of the Q. Since I need to find I equal to Q upon T, so Q I already got. Now I have to figure it out time T. Now all the electrons which enter the conductor at right side end, and they will leave on the left side. Suppose if I can take the diagram, if you can take this as, look at closely. Now the electrons are entering to the right and electrons are leaving from the left. To calculate the time, so we can use the very basic formula of time. So we know the drift velocity of the electrons, velocity equal to distance upon time. It's not drift velocity, it's just distance upon time. So from this, the electrons we are calculating. So electrons are having the drift velocity, that is the v suffix d, equal to distance. What is the length of the conductor? Distance is nothing but here length of the conductor. L is the length of the conductor and t is nothing but the time taken by the electrons with velocity vd to cross the length L. So from this expression I can write the time t equal to L upon vd. So that is the expression for time. Since I can express that at here, the electrons will enter, the electrons will enter the conductor at the right end, will pass through the conductor of length L with drift velocity vd, with velocity you can take it, with velocity vd, so that is the drift velocity, and leave at left end. Therefore time t equal to you can write upon time t equal to distance upon velocity. Here the distance equal to L and the velocity equal to drift velocity. Now I got t equal to L upon Vd. So this is the expression for time. Now by using these two expressions, can I find that current? Yeah, now it's easy. Therefore current I equal to Q upon T. Q equal to, what is the expression for Q? NEA times L. So Q equal to, I got it, NEA times L upon T. T equal to L by Vd. So you can cut the like terms, L gets cancelled. So now we got the new formula for current, that equal to NEA V suffix D. So current I equal to NEA V suffix D. So this is new expression for current other than from Ohm's law. Now here we remember, so all the characters are very easy to remember. Here n, capital N, small n, here the lowercase equal to n is nothing but electron density. Small n equal to electron density, and E equal to charge of electrons, and A equal to area of the conductor, and Vd is nothing but the drift velocity of the conductor. Now this is new expression for current. Now from this, can I define current density? Current density. Current density is nothing but J. Current density is J equal to current per unit area. Now I upon A. So from this expression, if I can write I upon A equal to, so I can use this in bracket, current density J equal to I upon A, which equal to, in this left side, which is the leftover terms, NEV suffix D. So another formula for current density. So J equal to NEVD. Now these two are the two new expressions. Till now we learned current I equal to rate of flow of charge q upon time, and current density J equal to current per unit area. So today we got new two expressions in terms of drift velocity. Current I equal to N E A V D and current density J equal to N E V D. So by using that above expressions, I would like to deduce Ohm's law. So let us deduce Ohm's law. What is Ohm's law? Simple relation V equal to IR. But right now we changed the I expression. I here as changed as in terms of current density and charge of electrons and area of cross section and drift velocity. Now we would like to change Ohm's law in terms of drift velocity. For that, I need to write the expression for potential, and we know the expression for drift velocity. Drift velocity E equal to V suffix D. Drift velocity V suffix D equal to minus E tau upon m. Here m is the mass of the electron and tau is the relaxation time and E is the electric field and capital E is the electric field and little e is the charge of electrons. Here the V suffix D. Suppose if I consider only the magnitude, so in this magnitude what happens? So the negative sign tells about the direction of the drift velocity, which is the opposite to the electric field. I will consider only the magnitude. Therefore, for only magnitude, drift velocity Vd equal to E tau upon m. And from the very beginning equation, the relation between, I want to know the electric field. What is the electric field is set up in this conductor. So the electric field set up in this conductor. So if the V is the potential which is applied to this conductor, L is the length of the conductor. So the electric field which is set up within the conductor. So the expression for electric field E equal to V upon L. So I will use that expressions at here. Since E equal to V upon L, that is the relation between electric field and potential. So in the place of this electric field, I can plug in that value. So the drift velocity Vd equal to E times V tau by L times small m. Okay, let me write this as little clear so that you don't get confusion. So potential Vd equal to E V tau by m times L. Now here I got the potential. So I got the potential. And now I have to relate potential and current. Since current I equal to NEAVD, now let me take this as first equation. Oops. Let me take this as first equation and second equation. If we substitute Vd value at that, so 1 into, therefore I equal to NEA. In the place of Vd I can get that E V tau upon m times L. Now we got voltage potential difference on one side and current on other side, and rest of the terms will becomes another terms. So if you can rewrite these expressions, I will write that I equal to N E square A tau v upon ml. Now I can write v by I. So I will bring this ml on this side, ml upon n e square a tau, which equal to v upon I. So this is v upon I is nothing but something like Ohm's law. So if this is v upon I, whatever this right side character, and this character is nothing but, yeah, it's resistance. So now this entire factor, so this total factor which equal to the new formula for resistance. Therefore, new formula for resistance R equal to, resistance R equal to M times L upon N E square A times tau. So this is the new formula for resistance R. So till now what we learned, so we are getting new expressions, like current we got new expressions, and current density also we got new expressions. Now we got new expression for resistance. Now let us see some manipulation at here. Now we know that resistance is directly proportional to length of the conductor, and resistance is inversely proportional to area of cross section. So I got that two characters at here, length L and area of cross section A at here. Now if we can write these expressions little more clearly, so R equal to, by rearranging the denominator terms, m times n e squared tau times L upon A. Now if this is the resistance R expressions, what shall I call this one? Now this character m upon n e squared tau, what would be this? This is nothing but resistivity. Why? Because from this expression this side I can write that resistance is directly proportional to L upon A, and the resistance R equal to rho times L upon A. So we said that rho is a constant. So what is that constant at here? So here the rho equal to m upon n e square tau. Now clearly you can look this. So this is having all constant parameters. M, mass of electron, yeah, it's a constant. N is the electron density, obviously it's a constant. For a given conductor, electron density do not change until unless if you change the length and the area of cross section of the current conductor. And E, charge of conductor, that is also do not change. And tau, relaxation time. Yeah, if you are maintaining at a particular temperature, the tau is also do not affect. So tau do not affect at all. So if you can write that expression for resistivity, so the new formula for resistivity, so this is nothing but resistivity. So factors which are affecting the resistivity, so on which factor the resistivity value depends. So in this in these four characters in the given expressions, so this is little more important. So the resistivity obviously depends upon, resistivity rho is depends on, it only depends on two factors. One is n and another one is tau. What is the n? N means nothing but the free electrons per unit volume or electron density, and the tau is nothing but the average time between two successive collisions. If these two characters has changing, electron density or the relaxation time tau, Obviously the resistivity value changes. If the resistivity value changes, resistance value changes. If the resistance value changes, the current flowing in the conductor, that's value also changes. Now here the very important factor, that is nothing but resistivity rho. Ask a question at here, how we can change resistivity without changing the size of the conductor or electron density. If electron density is constant for a given conductor, I would like to increase the resistance. So to increase the resistance, so from this resistivity rho, I can write that resistivity rho equal to m upon n e square tau. So here this little fellow is plays a key role. But this is that this is a relaxation time. What is relaxation time? The time taken between two successive collisions. The time taken between two successive collisions is known as relaxation time. Suppose if I do some action, this relaxation time is decreased. If relaxation time decrease, so from this expression I can write that resistivity rho is inversely proportional to tau. If the tau value decreases and the resistivity value increases, and if resistivity value increases, whatever the resistance value increases. If the resistance value increases, what about current value? Current value decreases. I can see the relation. If resistivity value decreases, the relaxation time taken between two successive collisions, if that value decreases, the resistivity value increases. If the resistivity value increases, resistance value increases. Why? Because resistance R equal to rho upon L upon A. Resistance is rightly proportional to rho, resistivity. And if resistance value increases, from Ohm's law, current value decreases. Okay, now how this relaxation time value decrease? How this relaxation time value decrease? So that is a very important factor, the factor of temperature. Factor of temperature. What is the factor of temperature? What the temperature can do? If you apply the potential difference and give the temperature, or if you can take, we are doing the experiment in winter season and in summer season for a given conductor. So in winter season the temperatures are low, so we can expect that relaxation time value is more time taken between two successive collisions because room temperature is less. But in summer season temperatures are more. If the temperatures are more, what happens to these electrons? Electrons will quickly, very fastly do the collisions. They do very fast collisions. If they do very fast collisions, so what shall I write that expression for tau? The relaxation tau value decreases. So when temperature increases, when the temperature increases, tau value decreases. When the temperature increases, tau, relaxation tau value decreases. When the tau is decreases, everything is relation. When the temperature increases, the relaxation time, tau value decreases. When the tau value decreases and the resistivity value increases, When resistivity value increases, resistance value increases. When resistance value increases, current value decreases. Wow, what a chain relation. It's something is mind blowing. See again carefully. When temperature increases, relaxation time tau value decreases. When tau value decreases, resistivity value increases. When resistivity value increases, resistance value increases. When resistance value increases, current value decreases. So this is the one of the major factor, the factor affecting the resistance, the factor affecting the resistance, that is nothing but temperature. Hidden factor, we don't consider that, but this is very hidden factor. So right now at here I am throwing a formula for you in terms of resistance temperature formula. Resistance R suffix T. I am thinking whether to do it now or not. Now I am thinking it's not right time, so because I already gave enough and more stuff and everything is very very important. So today's class I gave a new different formulas for current. Current I equal to NEAVD, and after resistance R equal to ML upon NE square A tau, and after resistivity rho equal to M by N times E square tau. And finally I open up that the factors which are affecting the resistivity, that is nothing but relaxation time. The main factor relaxation time depends on temperature. When temperature increases, the relaxation time tau value decreases. It is something, analyze it carefully. So resistivity value increases, obviously the resistance value increases, finally current value decreases. So this is all the relations between drift velocity and current. There I started. Then after we converted that in terms of Ohm's law, then we got new formula for resistance, and then after new another formula for resistivity, and which are the affecting the other factors.